Hi everyone, my name is Carlos Dominguez, and I'm here virtually with my colleague Stas Volkov. We were both in the GPA team, and we're going to be talking about game performance profiling with Intel GPA. Today, we're going to be talking about some workflows that we've been identifying that hopefully will help you gain a deeper insight on your application's execution and its impact on the system. We're going to be starting with an introduction of the tools that we're going to be using, the tool suite of Intel GPA. Then we're going to be moving on to a basic profiling workflow just to set the context on the more complicated, workflows that we're going to be talking about. We're going to start with a cross-tool performance analysis. We're going to talk about some of the pros and cons of the collection mechanisms that some of the tools have and how leveraging them in a synergy could hopefully give you more insight into your application. Then we're going to be talking about the multi-frame analysis, which is one of the newer features that we've added to the GPA tool suite. And then the newest tool that we've added to the Intel GPA tool suite, it's the GPA framework. And with that, we're going to be talking about automated performance reporting and how we managed to achieve this using the GPA framework. So, Intel GPA, what is it? So, GPA, hopefully you're familiar with it. GPA is a suite of graphics performance tools developed by Intel to help you optimize your games and graphics applications. I'm not going to be going through all of the different tools right now. I'm just going to introduce them as I need them. But it's just worth noting that they actually support all the way from DirectX 9 through 12, Vulkan, Metal, OpenGL. It actually works on Windows, Linux, Mac, and it also runs on all major PC graphics hardware. So, uh, good one too. And we've actually added a bunch of cool new features in 2020 R1. So hopefully I can actually talk about that a little bit later on. So for now, I'm just going to be moving forward to the basic profiling workflow. So this is a workflow that I've actually mentioned. I actually talked through it in the last GDC presentation in 2019. The link is down there in case you want to take a look at it as well, because I went into more in depth on each one of these stages. But what I wanted to show is like perhaps for a person that is not necessarily familiar or wants to kind of like structure their profiling workflow a little bit more. I wanted to show some of the different things that you could do and which tools you would be leveraging to achieve those goals. So, for example, we use a system analyzer, which is a real-time tool that gives you both system-wide and per-process metrics to identify the scene that we wanted to focus our efforts on. That would mean like all the point of views, perhaps the different levels, maybe a combat scene, something like that, or something that can get overlooked is like look at the different graphic settings that you can be using. And then once you identify the scene that you want to use, then you can go into Trace Analyzer, which is a deeper inside tracing tool that will give you much more high granularity data. And just a very, very easy way to figure out if you're CPU or GPU bound just by looking at how starved or fed the GPU is at a given point in time. And then from there, depending on if you're CPU or GPU bound, if you're CPU bound, you can do some more light CPU profiling with Trace Analyzer before you go into deeper analysis tools like VTune. And then if you're GPU bound, you use Frame Analyzer, which is the GPA's frame debugger profiler. And we're trying to make it as easy as we can on the Frame Analyzer team to at least help you understand some of the more basic questions, right? Like if you have a frame, we gather everything that went into creating that frame, all the shaders, programs, textures, etc., and help you understand first what are my most expensive draw calls um, or passes if you have debug regions enabled, and where in the graphics pipeline the bottleneck is. And for that, we leverage one of GPA's cool features that is called automated hotspot analysis that will run through some metrics and then basically tell you on the graphics pipeline where the bottleneck for that particular draw call is. So as you can see in this workflow here, I'm using each tool for some specific purpose. And while this is perfectly valid, it's worth noting that once you start understanding more the nature of the collection mechanisms that we use for the different tools, you can actually start leveraging them in synergy a little bit better to actually get more information out of them. And that's the first thing that we're going to be talking about today. I'm going to leave it now to Stas to talk about the cross-tool performance analysis workflow and how you can gain deeper insight on your application's execution.
Thank you, Carlos. So, as the GPU architecture evolves, it becomes more and more parallel. And if previously you had render and compute work running separately, now use an async compute feature in modern APIs, such as DX12 and Vulkan. You can have them running in parallel in different contexts. And inside each of such contexts, there is a massive amount of draw calls running in parallel as well. And therefore, all of this uses hardware differently compared to less parallel use case, for example, which was on previous generations of the hardware. This in turn brings new performance profiling challenges, as you not only need to look at performance of individual draw calls, but also you need to take into account the coexistence and co-execution of draw calls on GPU as well. So in this presentation, I will use trace analyzer and frame analyzer to profile the application, and I will show that usage of them both allows you to look on the same performance problem from multiple angles, and therefore increase your efficiency of your profiling and gives you more data. So the trace analyzer is the tool which provides you accurate timing and profiling data, and it shows you the CPU, GPU, and also it was extended by the parallel execution, which shows you how your individual draw calls were invoked on the CPU and when they were executed on the GPU. And this is the feature I'm going to use extensively over the course of this presentation. The downside of the trace analyzer is that it's really limited in terms of how much data it can show. The frame analyzer, on the other hand, it's not limited by this, as it replaces a sequence of graphics commands, and therefore it can provide you with all the metrics available on particular hardware, as well as all the states and resources being used across the execution of the frame. The disadvantage of the frame analyzer, on the other hand, is that it's limited to the GPU analysis only, and also it does not guarantee you exactly the same execution on the GPU as it was in your original application. And so using them both, you would get the best sides of them at the same time, and as I mentioned, this would increase your performance profiling efficiency. So in this presentation, I will be using Unity 3D Game Kit running on the Kaby Lake. This is a sample which is being distributed by Unity, and therefore you can replicate everything which I'm going to show. So I have an debug regions enabled in this sample, and therefore I can find the same render passes in frame analyzer and trace analyzer, I will be showing examples of 3 such render passes. The first one will be reflections, which is an example of really good parallel execution. The second one will be render shadow map, which is an example of less optimal parallel execution, and we will discuss why this is so. And the third one is post-processing and overlay, which has a sequence of draw calls which are serialized. So reflections, as I mentioned, this is an example of really good parallel execution, and this is like a good case, but there is still a problem. So while thread occupancy is really high, it's almost 96%, meaning that execution unit slots are almost fully used. There is a really high stall, which is almost 27%. And looking at these metrics, you can immediately see that there is some problem with accessing resources. So let's go to the frame analyzer and see what's happening here. When you find the same region in the frame analyzer, you will immediately see that there is a bottleneck, which is an L3. So this is indeed a memory bound render pass. So one thing to note in particular is that the sampler is marked as a secondary bottleneck. And when you have a memory bottleneck, the sampler is a first suspect. So let's look on individual draw calls inside this region. When you do select individual draw calls, first of all, you will see that iterate occupancy for individual draw call is rather high, as well as stall is around the same values for the whole render pass. So what thread occupancy is good. The potential problem with this is that every draw call in this render pass is trying to use this hardware resource at the same time, so they're conflicting for this resource. And so you need to just keep this in mind and possibly optimize around this. Each of these draw call has a bottleneck in L3 or DRAM, and each of them has a sampler inefficiency. And if you look on the metrics, you will see that sampler input is twice as large as sampler output, meaning that the sampler outputs twice less than there is on its input. So it's rather struggling to process all the requests. In order to understand what's generating this traffic, you can use a shader profiling feature, which is a new addition of the current GPA release. And because each call inside this render pass has the same shader, you can optimize the shader once and get the benefit of this optimization across all of the draw calls. For this particular shader, there is no source code, but even having the assembly, you can still get lots of data. So, for example, here you can see that 5 sample operations are taking most of the latency of the shader execution, and the largest one, which is at the end, if you look more carefully what resource it belongs to, you will notice that it's a cube map texture being sampled. So the general advice for this one would be try to change your resources to optimize access to them. Try to use different format or different dimensions, or altogether like restructure your resource usage. The next region is a render shadow map, and this is an example of a sequence of really small draw calls. There are 3 such areas, and this is not the worst parallel execution case, but it could be better. And so we will try to see what's going wrong here. But before we move into the frame analyzer, if you look on the metrics, you can see that the stall is quite large as well. In this case, similar to the previous example, it's 32%. But it's not the main problem here. The main problem here is that thread occupancy is rather low, and this is the primary reason why EU stall is also high. There is just not enough threads to hide the latency of accessing resources. And so because the thread occupancy is so low, you can make an assumption that there is a bottleneck somewhere in the geometry pipeline. And let's look on the frame analyzer to see if it's the case. When you find these draw calls in the frame analyzer, you will immediately see that the metrics viewer shows you that there is a geometry transformation bottleneck. You can also see a quick tip of what you can change, as well as a link to more information where you can go and have a more complete set of advices on resolving this bottleneck. In the resource panel, you can also see that there are more than 300 meshes, so there are lots of geometry being processed. And if looking at the metrics as well, you would notice that the vertex count is almost 11 minutes. And if you compare to the whole geometry and whole vertex number being used across the whole frame, this is 78% of the frame. And the polygon data ready, which is an output rate of geometry pipeline, is 54%, meaning that it's on average outputs only every second cycle, so which is not great as well. So to summarize, there is a geometry processing bottleneck. You can try to batch your draw calls together. This would reduce the number of commands being recorded to the batch buffer, as well as would increase efficiency of the Vertex cache usage. Additionally, the good advice would be also try to just minimize the number of geometry being passed to the GPU. Maybe try to get rid of the objects which do not contribute into the final render target by pre-processing this geometry on the CPU. And the last region which I want to show you, which consists of two subregions, is post-processing and overlay in the trace analyzer. And here, if we're speaking about post-processing first, you can see an example where there are 24 calls being executed sequentially, so they are all serialized. And the primary reason for this, as you may see in the frame analyzer, is that there are frequent render target changes. So you can see this by enabling the mode on the frame analyzer bar chart, where your render target changes are represented as dashed lines. And so as you can see, there is a render target change after each draw call, except two calls at the end of the render pass. But here there is another problem. The two draw calls which use the same render target, they are draw and dispatch respectively. And when you have transition from draw to dispatch and then back from the dispatch to draw, in the middle the pipeline is flushed, meaning that draw dispatch sequence always executed sequentially. So we need to keep this in mind and try to avoid these transitions from rendering to compute and vice versa. The next subregion is an overlay. And there are two copy calls which combined take 207 milliseconds, and there are no other draw calls being executed at the same time. So you can understand why this is happening using Frame Analyzer and the resource history feature, which is a part of it. And there are two resources being involved. The first one is 151, let's call this resource 1. The second one is 1213, let's call this resource 2. And if you look into the first copy call, resource 1 is bound as input, and resource 2 is bound as output. On the draw call, after the first copy call, the resource 1 changes its binding and becomes an output, and resource 2 becomes an input. On the second copy call, they change their bindings as well, becoming input and output respectively. And on the fourth call, on the next draw call, after the second copy call, they become output and input respectively. So as a general advice, you should try to avoid frequent changes of the render targets, or having dependencies between the render targets at the same local place of the execution. Try to spread these dependencies over the timeline and use some draws in the middle which are not dependent from the resources in question. And this could overall increase your parallelization. So as a conclusion for this part of the presentation, again, I wanted to say to use Trace Analyzer and Frame Analyzer together. This will give you more data than usage of just a single tool. And at the end of this whole presentation, there will be a link to Intel GPA Cookbook, where you can find more examples of profiling and more examples of usage of different features in the GPA tools. So feel free to try this out. And now I'm transferring the speech to Carlos, who will tell you about other really great features which are added into the GPA on the recent release.
Thank you, Stas. So moving on, our next deep dive is going to be the multi-frame analysis workflow. This is actually something that is really exciting for us because it's been arguably the largest change that we've done in GPA in recent history. So we want to talk a little bit about what this is, what kind of problems we're trying to solve, and what prompted us to take this endeavor. So as we've been seeing throughout this presentation, we've been looking at our typical workflow, which is our single frame capture mode. You launch your game, you play through your game until you get to your frame of interest, then you capture your frame. That generates this file that has all the resources that are needed to basically replay that one frame over and over again so that we can collect different metrics and whatever we need to present in the frame analyzer UI so that you can identify your hotspots and profile and debug your application. So one of the things that we set out to do with the GPA team was, what if we could capture not only one frame, but what if we could capture all frames? So part of the reasoning here was, if we can create a reproducible scenario at the graphics API level, we can present the whole stream, the whole playthrough to you in the new multi-frame view. And then that way you can carefully select the frame that you would want to capture and then open it up in Frame Analyzer in the tool that you're already familiar with. If you want to open 2 frames, that's fine. You want to open 1 frame in Frame Analyzer, that's fine. But that way you have the one reproducible scenario at the graphics API level that you can pick your frames from. So why would you even want to do this? So one of the things that we set out to do with this new mode is we know that there's some inherent issues with trying to capture just a single frame. Some of these things are just, some of the problems that you are trying to tackle are virtually impossible to solve with a single frame capture mode. If you have something like intermittent glitches, where you have something that's just flickering on the screen or something like that, just grabbing the one frame that exhibits this behavior can be a little bit difficult, and you kind of like have to rely on lock when you just have the one shot to capture a frame. Also, like if you have like a certain frame drop at some point in the game, that can be really hard to debug if you wanted to analyze why is this happening. Or even just like more modern algorithms that you may not actually be updating a particular render target or something like that every frame. Like let's say that you have like a shadow pass that only updates the shadow map every other frame. So if you wanted to profile that, you would need to rely a little bit on lock and getting the actual frame that you would want to capture. So what we did here is we present you with this whole stream-wide data and with GPU durations, and we can correlate it with a few of the things that we get at capture time, like other metrics that we can collect. And that gives you that scenario where you can actually grab the one frame of interest and then just dive into it. In this case, you can see that we select one of the bigger frames so that we want to analyze why that particular frame is actually much larger than the rest, if it should be around the same ballpark. But one of the things that is most interesting to us about this new backend is that it is what it is. It's a new backend. And what we did with this new backend, we decided to productize it into what we call the GPA framework. The GPA framework is the newest tool in our family of tools within the Intel GPA tool suite. And what we did with the framework is grabbing this new backend and basically allow developers like you to use it for perhaps like just giving you the opportunity of using what GPA uses to gather all the performance data, all of the capture and playback mechanisms, basically everything that we do to populate the GPA UI. But since you already have additional knowledge on your workload, like you know exactly the names of your debug regions, you know the passes that you have enabled, kind of like the way that your scene is structured, we don't necessarily have that data. So when you look at GPA, we have like a more generalized approach of what we can show in the tool. But this allows you to hopefully create more like in-house tools that are catered for your particular use case. This is actually a good segue to our next section, because in the next section, I'm going to talk about an example of how we can use this GPA framework for one particular use case, which is creating automated profiling reports. So I decided to do the automated performance reporting as the use case for the GPA framework for two reasons. One, it's because I think this is a good use case to show the kind of data that you can get out of the framework and how you can use it to catch performance regressions and things like that using the constructs that we provide in the framework. But also because I think this helps us address some of the problems that are inherently hard to do uh, when we want to try to incorporate more performance profiling earlier in the development cycle. Um, that can be very prohibitive. And as we know, I mean, because it's very time consuming, it also requires quite a bit of domain knowledge, which means that perhaps just a few people in our team will actually be able to do this performance analysis. And these people are usually not necessarily full time doing performance analysis, right? So you may not have the bandwidth to do this kind of stuff, especially if you add the permutation of testing on different hardware with different graphic settings, things like that. So um, that tends to make this type of performance analysis getting it gets pushed all the way to the end of the development cycle. And while I understand that, I mean, we have the quote of like premature optimization is the root of all evil, and we've all heard this. And while I do agree with it for the most part, I do think that when it comes to content creation, there's also you could also say that shaving off 10% throughout your development cycle of micro optimizations could actually be easier than just trying to get that silver bullet that at the end of the development cycle you're gonna manage to get some 10% speed up. That speed up may actually come at a compromise. It may come with a visual quality degradation, um, because everything at that point in time is kind of like set in stone. Usually you've already created all the content. You as a performance engineer, you most likely were not the person that actually created the content. So what I'm trying to propose here is that we shift the way that you this performance profiling and just generate more of like this performance awareness. And what I mean by that is just being conscious about performance at content creation. um, this actually makes it so that it can be a whole team effort where our artists can be very conscious about the things that they're adding to the game. Our designers, even our producers, could actually understand the health of the product throughout the development cycle in the different platforms. Hopefully, this could alleviate some of that profiling that needs to be done at the end of the development cycle, so that things get catched much earlier. And this is not necessarily like a novel idea. We do this a lot in engineering already with continuous integration, continuous deployment workflows. But this can get a little difficult when you're talking about content creation, as we know, because you need that reproducible scenario that you need to create, and then that means that you need some infrastructure to create this. Like there's some capturing and playing back. You need the access to the data that would give you the hardware counters from the GPU to gather the data that you need to create this reporting. So one of the things that I want to talk about here is how the GPA framework can actually help you with all these. But more importantly, this is just like the tip of the iceberg of the things that the GPA framework can help you with. The idea is that we wanted to expose this so that you can create whatever tools would suit your particular needs, because you know much more about your game than we do, right? We tend to do GPA in a more generalized way to cater to all games, but you know what the names of your debug regions so that you can actually parse them appropriately. You know the passes that you're enabling, you know the game engine that you're targeting. So that could help you do more specific tools for you. And what we want to do is just expose anything that we can to support you and help you in that regard. So this is what I came up with. This is by no means a full-on product. I just wanted to do just enough to show the framework capabilities. I'm going to be showing some snippets of code on how to get this in the Intel Dev Mesh, which is hopefully where you saw this presentation. Otherwise, it's going to be in the links. Well, what I set out to do here is I wanted to do something inspired by like a Jenkins type dashboard where you can do different playthroughs of your game, and then you can store them in some server, and then you can see your general health of your performance for that particular run. So what you see here, it's some stream-wide data that gives you playthrough-wide information, all the way to some particular frames where you can see the breakdown for that particular frame based on the debug regions. and you can see the time spent on each one of these debug regions relative to the parents and relative to the full frame. I also wanted to show something like texture statistics, so you can see an example of something that you can immediately see and flag like things that may be bad. Like maybe you're targeting like low settings, and then you suddenly see a 4K by 4K texture, and that shouldn't be. And then that's the kind of things that I wanted to go with for this performance profiling dashboard. Again, it's not to do a full-on product, it's just to show the kind of things that you can do with the framework. And we're going to talk about how I was able to get all this data with the framework. So just to take a step back from this is kind of like the vision that I had for the workflow. Say you have your Jenkins nightly build that generates the build for your game. Once that finishes, you can kick off this automated playthrough that somehow manages to create a gameplay reproducible scenario that with the framework we can translate that gameplay reproducible scenario to a graphics API reproducible scenario. It gets stored in the stream, and then somehow you get to play back that stream, play with the metrics, address some things, and create an automated performance profiling data dump that you end up using to report back to your dashboard. In my case, I just use a JSON file, a bunch of JSON files that you can just visualize in the report. With the goal here being that 90% of the time you can just go in every day and just say, hey, like just something minor, like, hey, like maybe someone forgot to create an LOD, or like the example that I gave before, like this is a low settings run. Why are we even showing 4K by 4K textures? That's you're probably going to be sampler bound, that kind of stuff. And some of the cool things, well, one of the other things that could be not necessarily obvious, let's say that us also, just so that we don't only blame the content creators, as a graphics programmer, we could be optimizing a shader for a particular scene, and that shader may be used in some other scene that you weren't actually testing. You may have improved performance of a particular shader in a scene, but maybe in another scene the performance actually dropped because the optimizations didn't carry over there. So one of the cool things about this too is that you can keep all those streams in the cloud, so that, like I said, 90% of the time you don't even need to pull them at all. But if you needed to do some additional performance profiling, you can grab those streams, bring them to your computer, and then do some further analysis because you basically generated that reproducible scenario at the graphics API level. So we're going to go through all of these things. All of the things marked in orange are the things that we can help with the framework. Automated playthrough is going to be one of the tricky ones because there's an aspect that you'll have to do yourself and one that you will be able to leverage the framework with. So to create an automated playthrough at the gameplay level, there's a few avenues that we can explore. Some of the more obvious ones would be perhaps a benchmark that you may set up in your game, or some custom scene. Maybe, and the approach that I took for my particular small test was I used one of these gameplay unit test systems to generate a reproducible scenario at the gameplay level. That is the one part that GPA Framework will not be able to help you, and you, with the knowledge of your workload or your game, you will be able to generate this, hopefully. Because once you do, then we can take it from there. You can leverage our GPA injector tool, which allows us to inject our own layers. One of the layers is the capture layer, the same one that GPA uses, that dumps out this playthrough of the stream. And that's what becomes your reproducible scenario at the playback level. Why at the playback level? Because now we can actually use the GPA player and the playback layer to reissue all of those commands to the graphics driver. And then from the point of view of the driver, there's no difference where these commands came from, either your game or from the stream. So once we get that data and we have this stream, we have this reproducible scenario at the graphics API level, we want to be able to somehow extract this performance data, right? We want to automate this performance analysis somehow. We want to take that stream, we want to pass it through some black box, I guess, that ultimately what it does, it gives you some performance information. In my case, like I said, it's just a bunch of JSON files that it's what the report uses to report back to the user the current health of the performance profiling health. So these can actually be achieved in different ways with a framework. And I'm gonna go through them just to show kind of like the pros and cons, like everything. It has each one of these have pros and cons. So I'm gonna go through each one of these and then talk about the one that I actually ended up using. So the first one is you can actually write your own custom layer. So one of the things that we did with the framework is allowing you to create your own layers. Like we expose our capture and playback layer. We also give you all the tools that you would need to create your own layers and use them in the same way that we do our own. This would be what I would consider the most manual approach. And manual because you wouldn't be able to leverage any of the constructs that we use in GPA, for example, to populate the UI and stuff like that. And you would basically, what you would need to do is intercept all of the calls that you're interested in. You would need to instrument them yourself. And one of the biggest drawbacks is that you wouldn't be able to leverage our range repeat mechanism, which allows you to select the range and just repeat it many times, collect many metrics. But the biggest advantage of this workflow, though, is that if you take the time to create your own layer, these layers can actually be used both at playback and at capture. Well, not capture time, but at gameplay time. So you can actually run it right from your game and still get some performance statistics from your runtime execution. So that could be an avenue. That's not the avenue that I took for my workflow. I ended up using the C++ interfaces, which is the other way that we can grab this kind of data. Either the C++ or the Python interfaces, which ultimately what this means is that you have either a standalone executable if you're using the C++ interfaces, or a script if you're using the Python interfaces. And what they do is the first drawback is that it only works at playback. If that's not a problem for you, then that's fine. It wasn't a problem for me because this is the model that I wanted to follow for my continuous integration system. And this actually interfaces with this thing called the playback engine, which we're going to be talking about a little bit later on, which handles all of these range repeat that I just mentioned, how to play the stream, how to interface with the driver, to basically service all the requests that you are giving it to gather any textures or metric collection, etc., etc. And then with this executable, you can gather all that data, and then you end up creating your own perf stats that you can then show in the UI. So I will not go through a lot of the code of what you can do with GPA framework. My goal here is not to show how does the code look or the architecture of the code. Is more about the kind of things that you can do with the framework. That said, I do want to show, like I promise it's just gonna be a few slides to show the kind of thing, the code, just to show just kind of like how it looks, so you get a good understanding, or at least a basic understanding of what to expect from the framework. And so what I'm showing here is a Python interface example of, all I want to do is print all of the APIs that are within the 20% to the 40% of the stream. Let's say that I have a stream that has 100 frames. That means just basically every API call from the 20th frame to the 40th frame. And you can see that it's as easy as just opening the stream, getting that particular range, iterating through the callables in the range, and printing out the name. So it's not necessarily rocket science there. A similar example in C++, you see that it's not much larger, really. In this case, instead of doing a range, I'm just doing one particular frame. I'm just looking at all of the API calls in frame 100. And you can see that the workflow is actually very similar. And one of the cool things about this, too, is that you don't need to start from scratch. We actually have a bunch of samples. One of the things that we did when we decided to productize the framework was to be able to give you enough samples for 90% of the things that you may want to do with the framework, at least just to get you started. And as you can see here, I have the print API log sample that I just talked about. There's a couple samples with the layers. There's a bunch of other examples of how do you use the framework to get shaders, get textures, get apply experiments like the ones that you can do in GPA, collect metric data, all that kind of stuff. And as a matter of fact, for this dashboard, all I did was hack away and stitch together these three samples. And that's one of the things that we're going to be talking about here, how I managed to do that, what kind of things I had to do to modify the samples, which is going to be very, very, very trivial. And you're going to see it too in the dev mesh snippets that I will be posting as well. So before we get into those samples in particular, I want to show some of the way that I got all the stream-wide data. This stream-wide data was gathered through a couple of utilities that we get in the framework as well. What you're seeing here is in the left side. What I wanted to do, like I said, was show the different runs that you did from your game playthrough. And I wanted to show a sparkline just to show at a glance what would be the current health of your performance for that particular run. And what I did there is using this frame time distribution curve, where you can see the percentage of frames that were below or above a certain threshold. So the one threshold that I put in here was that this red line, it's the 30 FPS line, which is the 33 millisecond line. So in this case, you can see that at a glance, you can see that this one particular run was really bad. Only like 5% of the frames ran below the threshold, and all of the other ones actually performed pretty bad. But this is the kind of data that you can get from the GPA stream analyzer, which will dump out all of this in a JSON file that you can just parse and visualize it this way. Another utility is the GPA stream info, which actually gives you all of the information in relationship to that one particular stream, which is what driver you were using, what graphics hardware vendor you were using, the resolution, as you can see here, the number of frames that you captured, all that kind of stuff. And the GPA stream info actually has much more information. I just showed some of the more representative ones in here. So once we get all this stream-wide data, we can dive into how we got to populate the dashboard for the frame-specific stuff. So the first thing that I wanted to set out to do is get a breakdown of all the hierarchy of all the debug regions. So this was actually very simple to do. As a matter of fact, this is the last slide that I have with code, and the only reason why I'm showing this is because this is a modified version of the example that we saw above, sorry. But instead of just grabbing the name, in this case, there's another property called the category. And the category is a mask that tells you what kind of call this callable is. So two of the types are begin user region, end user region. And with that information, that's enough to do this whole breakdown, and you can create a fancy little view like the one that you see on the right side. In the same way, you can use all the other categories to create the statistics that you see here, because all the other categories are, is this a clear call? Is this a copy resource call? Is this a dispatch call? That kind of stuff. And it's actually pretty simple with the print API log example. So once we have all of these debug region breakdown, it really doesn't help a lot to just have them raw like that without understanding how long did they actually took in the GPU, how long did it take in relationship to their parent, and how long did it take in relationship to the whole frame. So with that, we're going to involve another mechanism that the framework has, which is the playback engine that we mentioned before, and particularly the metrics extractor. And that allows us to create this flame graph type thing that allows you to see with true GPU duration how much each one of these debug regions, which are the different passes or whatever, take in relationship to the parent and in relationship to the frame, and then you can see what are the most expensive regions in your particular frame. One of the things that is worth pointing out here is that this playback engine that I mentioned before, it abstracts all the collection mechanisms, like I said before as well. So when you do a metric request and you say, hey, give me all the available metrics, if you're running on Intel hardware, this is going to run through this collection mechanism called MDAPI, which is what we use in GPA. It gives you very detailed metrics of the Intel hardware. But say that you're running in a third-party hardware where you don't have access to these metrics, we still can collect some data, namely pipeline statistics and timer queries, so you can still get GPU duration. You will not get the level of granularity of data that we get in MDAPI, but you do get some stuff. And the idea here is that the playback engine abstracts everything for you. So when you do a request of get me all available metrics, it's just going to give you a list no matter where you run it, and it's just going to take care of all these dependencies. When you do a request of actually collecting metrics for a particular region, it will also handle, you say, hey, give me the metrics, the X metric, Y metric for this particular region. And it's also gonna take care of replaying that particular range as many times that it needs to collect all the metrics that you may need. And that's how you can create this call stack breakdown. Now, moving on to the next thing, it's the another mechanism that we're going to be using is the metadata extractor, which is similar to the metrics extractor. But first, I want to talk about what exactly is metadata. Metadata, it's all of the data associated with a resource that is not necessarily the data itself of the resource. So when it comes to a texture, it's not necessarily the actual texture data, but it's more of this data associated with it, which is the resolution, the X and the Y axis, the format, all of these data associated with the texture. So with this data, we can actually extract it with a metric extractor, and we can create a distribution graph that could hopefully, like I mentioned before, help us flag problematic usage like big textures or keeping a good eye on the uncompressed formats that we may be using, make sure that we don't overuse them, etc., etc. And this data is we can correlate with one last part that I actually didn't get a chance to actually play with for this dashboard, unfortunately. But hopefully I can append this to the dev mesh later on. But it's how can we act on this data? I think it would be really cool, and it's actually all of the things that you need for this are in the framework already to be able to flag this type of resources like the textures, and then you can do something like look at a 4K by 4K texture, for example, and it's a low settings playthrough. So you can actually apply the texture 2x2 experiment that comes with GPA, and then you can actually run it, do more metric collection, and then when someone comes in the morning and sees that there was a texture flag, you can see, hey, this texture was flagged, but also you can see this could give you this type of performance gain if you were to tackle this problem. Of course, that would be kind of like the best case scenario, but at least it would give you some information to see what would be the things worth pursuing. So that's basically it. That's all of the things that I did to create this dashboard. So as you can see, all of the things that you need are actually in the framework with samples associated with it so that you can grab the data that you need. I'm really excited to see what kind of things you can come up with. Hopefully you tweet about them or just share them with me somewhere, because I want to see what kind of tools you can build on top of the framework. And just to wrap up, I wanted to mention once again, performance awareness is everyone's responsibility. Hopefully within the GPA team, we're doing our part to give you all the data, all the tools needed so that you can act upon this. Also, I want to stress out that Intel GPA is more than just frame analyzer. I do this. One of the problems that I have myself is that I tend to refer to GPA as frame analyzer, but as we saw today, it's much more than just frame analyzer. And not only that, just understanding the difference and the pros and cons of the collection mechanisms of the different tools could actually help you get just more insight into your game's performance. I hope you try out the multi-frame analysis workflow. It is fairly new, so any feedback would be really good for us. We would really appreciate it, and hopefully we're on the right track moving forward. And I hope that you can, employ some of these continuous integration, continuous deployment usages with the framework. And again, as a reminder, this was just the tip of the iceberg. This is just one of the use cases that I thought would be cool to show. But I hope you can use it with other things, and I'm really looking forward to that. There's my Twitter account in case you want to tweet about it, and thank you.